In this video, we are going to design the singly reinforced beam by using codal rules. Design a reinforced beam of clear span of 5 meter to support a working live load of 15 kN per meter. Adopt M20 grade concrete and Fe4 and 5 steel and sketch the reinforcement details. What they have given, the given data are they have given clear span, that is small l is equal to 5 meter and load is equal to 15 kN per meter. Supportive width they are not given, but in our calculation it is necessary, so I am assuming support width is equal to 300 mm. And FCK grade of concrete they have given 20 Newton per mm square, and FY grade of steel they have given 4 and 5 Newton mm square. To start the problem, the effective depth is necessary for all the calculation, so we'll go for calculation of effective depth. So first step is to calculate the effective depth. As per cost 23.2.1, page number 37, what it says, let's see. Page number 37, 23.21. The vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratio are not greater than the values obtained as below. Basic values of span to effective depth ratios for spans up to 10 meter. For cantilever beam they have given 7. For simply supported beam they have given 20. So now we are calculating the simply supported beam. No? So what they have said our L by D ratio for simply supported beam should not be greater than 20. They have said. So now I am assuming I am taking L by D ratio as 12. I moved D to here. The L by divided by 12. The clear span value is they have given 5 meter. 5 meter is nothing but 5000 mm divided by 12. Simplifying this, we'll get 416.66 mm. So I am providing D as 450 mm. Why I am providing 450 mm means in our RCC often calculated values are adjusted to a standard dimension. So I am providing D is 450. So now next is to assume the effective cover, that is denoted as D dash. I am taking effective depth as 50 mm. So now we'll calculate the overall depth, that is denoted as capital D. Overall depth is equal to effective depth plus effective cover. 450 plus 50. We'll get after simplifying 500 mm. So our D is 500 mm. So next is to calculate the width of the beam. For that we have the formula B is equal to 1/3 of effective depth to 2/3 of effective depth. So I am taking B is equal to 2/3 of effective depth. 2 by 3 into effective depth which we have provided calculated, that is 450. By simplifying this, we'll get 300 mm. B is equal to 300 mm. After the calculation of width of the beam, we'll go for calculation of load, that is self weight of the beam. Self weight of the beam, we have the formula B into D into rho. Rho is nothing but density of the RCC, that is 25. B is 0.3 and D is 0.5. Rho is 25. Simplifying this, we'll get 3.75 kN per meter. So now we got self weight. After that we have to add load which we have got in our problem. They have given load is equal to 15 kN per meter. So to find out the total load, we have to add self weight of the beam plus load, that is nothing but 3.75 plus 15. After simplifying this, we'll get our total load is equal to 18.75 kilonewton per meter. After the calculation of load, we'll go for calculation of ultimate load, that is denoted as WU. This is also called as factored load. For this, we have the formula 1.5 into total load. 1.5 into total is how much we have got? We have got 18.75. After simplifying this, we'll get 28.12 kilonewton per meter. This is our factored load. After the calculation of ultimate load, we'll go for the calculation of effective span. Calculate the effective span as per cos 22.2a, page number 34. What they have said, effective span, unless otherwise specified, the effective span of a member shall be as follows. For simply supported beam or slab, the effective span of a member that is not built integrally with its support shall be taken as clear span plus the effective depth of slab or beam or center to center of supports, whichever is less. What they have said, to calculate the effective span, we should take clear span plus effective depth or beam or center to center of supports. But in our problem, we have got clear span plus effective depth and support width. So I am taking L is equal to clear span plus support width, and second one L is equal to effective depth. So we'll see. You can take whatever you got in your problem. So I have got support width and effect depth. So I am taking these two. L is equal to clear span plus support width. After simplifying this, we'll get 5300 mm. So next one is L is equal to clear span plus effective depth. Substitute the value. After simplifying, we'll get 5450 mm. They have also said the L value should be least of these two. So which is least? 5300 mm is least. So I am taking L is equal to 5.3 meter. In terms of mm, 5300 mm. This is how we calculate the effective span. So after the calculation of effective span, we will go for calculation of bending moment. We have the bending moment formula for simply supported beam, that is mu is equal to W L square divided by 8. Substitute all the values, we will get, after simplifying this, we will get 98.73 kilonewton meter. So mu is equal to 98.73 into 10 to the power of 6 Newton mm in terms of mm. This is how we calculate the bending moment. After the calculation of bending moment, we will go for the check for effective depth. So whatever the effective depth we are provided or calculated, whether it's sufficient to carry the load or not, we have to check. So that we have the formula mu limit is equal to 0.138 FCK BD square. I am taking it as D required. D required is equal to under root of mu divided by 0.138 FCK into B. Substitute all the values. Simplify this. We'll get 345.31 mm. So our D required is 345 mm. So our D required is 345 mm. So the D which we are provided is 450 mm. So our D provided is greater than D required. Hence our design is safe. After the calculation of D, we'll go for calculation of the mu limit. The formula which we have used for D check, that is mu limit is 0.13 FCK BD square. The same formula we are using for mu limit calculation. So mu limit is equal to 0.138 FCK BD square. Substitute all the values. After simplifying this, we'll get mu limit is 167.67 into 10 to the power of 6 Newton mm. Our mu value which we have got our bending moment value by using the formula WU L² divided by 8, we got is 98.73 into 10 to the power of 6 Newton mm. But our mu limit value is 167.67 10 to the power of 6 Newton mm. So our mu limit value is greater than mu. So NC, our section is under reinforced. When our section is under reinforced, we need to design the singly reinforced beam. This is how we'll calculate the mu limit. So next step is to calculate the AST. For that, as per G1.1b page number 96, so we'll calculate the AST, that is G1.1 page number 96b. Here is the formula of AST calculation, that is mu is equal to 0.87 Fy AST D bracket 1 minus AST Fy divided by BD FCK. By using this formula, we'll calculate the AST. So I have written same formula which is on page number 96. So substitute all the values and simplify this. After simplifying by quadratic equation method, we'll get the answer at 678.40 mm square. I will show how to solve this by quadratic equation. So using calci, at number 5 is equation. So I am pressing 5, and at number 3 is a square plus bx plus c is equal to g. A square plus bx plus c is equal to 0. So our equation is in the form of equation 3. So I am taking equation 3 and substitute all the values. That is, first value is 24.97, and the second value is minus. So minus, now I am taking bracket, minus 1624.72.5 bracket close, and after that 98.73 into 10 to the power of 6. So 10 to the power of 6. Substitute. So after simplifying, we'll get our AST value is 678.40. So this is how we calculate the AST by quadratic equation. So after calculation of AST, now we have to assume the bars. So you are free to assume any diameter of bar. After assuming the diameter of bar, we have to calculate the number of bars required to carry this area of steel. So I have assumed 20 mm pi bar. So the area of one bar formula, that is small, denoted as small AST, is equal to pi by 4 into pi square. Pi by 4 into our diameter is 20 square. After simplifying this, we will get 314.15 mm square is our area of one bar. So after this, we need to calculate the number of bars required to carry this area of steel. So number of bars is equal to AST. Our AST what we have calculated into number of bars. Substitute the value, we'll get, after simplifying, we'll get 2.16. So I am making it approximate 3 numbers. So 3 numbers of bars is required to carry this area of steel. After this, we will calculate the AST provided. So AST provided is equal to number of bars which we have calculated, that is 3 into our area of 1 bar, that is 314.15. After simplifying, we will get 942.45 mm square is AST provided. So provide 3 numbers of 20 mm pi bars at tension reinforcement. After the calculation of AST provided, we have to calculate the axial bar also. We need to calculate the axial bars is nothing but the actual bars we are going to provide. So again, as per your codal rule, as per clause 26.5.1.1 A and B, what it says, we'll see what is the minimum and maximum reinforcement required in a beam. So what it says, the tension reinforcement, the minimum area of tension reinforcement shall be not less than that given by the following: AST divided by BD is equal to 0.85 Fy. We need to calculate the what is the minimum reinforcement on this particular B and D. We have to calculate. After this, again we need to calculate the what is the maximum reinforcement. The maximum area of tension reinforcement shall not exceed 0.04 B into D. What they have said? They have said our maximum reinforcement should not be greater than 0.04 B into D. So by using these two formula, again we have to satisfy these two codal provisional by using these two formula. So we'll see. So by using this formula which is given on page number 46, that is AST minimum divided by BD is equal to 0.85 divided by Fy. So I am moving BD to here. After simplifying this, substitute all the values. After simplifying this, we will get 276.50 mm square. So our AST minimum is 276 mm. So now we have to calculate the maximum reinforcement. To find out the maximum reinforcement, we have the formula they have given, which is given on page number 47, that is AST maximum is equal to 0.04 BD. Substitute all the values. After simplifying, we will get 6000 mm square. So what they have said, our maximum AST maximum is 6000 mm square and our AST minimum is 276 mm square. So we should not provide our AST less than 276 mm and more than 6000 mm square, but our AST is 678.40 mm square. So our value lies in between AST minimum and AST maximum. So our AST is greater than AST minimum. So our design, because our value is lies in between AST minimum and AST maximum, so our design is safe. We have satisfied that these two are codal provisional. So one more codal rule we have satisfied. The